2.3, we're now going to work on Objective 8, graphing polynomial functions, which really is pulling all of the other objectives in this lesson together, with the exception of 1, identifying polynomial functions. Make sure you look back at that. There are just some rules. No dividing by x's, no negative exponents. Those are all part and parcel of other kinds of functions, but not polynomial functions. So take a look back at Objective 1. And Objective 6, using intermediate value theorem, we're not going to be talking about that with the graphing polynomials. That one kind of stands on its own and is normally a separate question asked in and of itself. So let's talk about Objective 8. And we're going to start with using this 5-step strategy. This is example 9. To graph f of x equals x to the 4th minus 2x squared plus 1. Okay, this is a polynomial function. And when you look at that, I want you to be able to look at a function when you go to take the quiz, when you have been working on your practice problems, and you need to be able to look at that and have some sort of idea in your mind what the end behavior of this polynomial should look like. Okay, and it all goes back to, is the polynomial of odd degree or is it of even degree? Okay, those will all, odd degree polynomials will all have similar behavior on the ends, and even degrees will all have similar behavior on the ends. And then we break it down into, is the leading coefficient positive or is the leading coefficient negative? Okay, and both of those pieces of information are going to come from the term with the biggest degree. Okay, it's not always the very first term in the polynomial. Sometimes we'll write the function with the terms all mixed up as far as degree goes to make sure that you're looking for the term with the largest degree. Sometimes they're in reverse order, so you need to just glance through your function and make sure you're looking at the highest degree term, and that means you're looking for the biggest exponent. So the exponent in the highlighted term is even, and so all even degree polynomials will have similar behavior to this. Its leading coefficient is positive. There is actually a 1 that is in front of this x to the 4th. Okay, we don't see it because it's a 1, but the 1 is there, and we use the 1 to say that this is this has a positive leading coefficient. So I'm going to show you this one right off the bat. When we get done with example 9, our graph should look something like this. Okay, if it's even, as this is, but our leading coefficient is negative, then it's going to look like that. Okay, just like with a parabola, we've always talked about, does it cup up or does it cup down? And it had to do with the a value being positive or negative. Same thing here. So even, think about a parabola. It's going to cup up or it's going to cup down. Positive up, negative down. Odd, you can think about that more like a line, meaning a diagonal line. A sloped line will either start down in the 3rd quadrant and rise into the 1st quadrant, or it will start maybe in the 2nd quadrant and fall down into the 4th quadrant. Okay, so it's either going to be low on the left, high on the right, or high on the left, low on the right. Here is what a line with a positive slope, that kind of behavior would be. Okay, yeah, it does some funny things in the middle, but overall, this is rising. And the negative is just the opposite. Overall, it is falling, except for that one little piece in the middle. Okay, so when you look at functions, I want you to get one of these 4 pictures in your mind. Sketch it out before you even start, so that you know when you're done, is my graph showing the proper end behavior? That's step 1. Step 2. The zeros and their multiplicities, like I talked about in the previous video for this lesson 2-3. This is a monster lesson. Okay, in the example we did before, you were given your function in completely factored form, and all you had to do was set each factor equal to 0 and state the multiplicities. This is not the case here. we have a function in expanded form, and we have to factor this ourselves in order to see those zeros. What is nice about this one is that we have this fourth power, second power combo, and then a constant back here. And that's helpful because even though this is not a quadratic equation, it is an equation that we can use quadratic techniques. And the reason we can use those is because the highest degree is twice that of the middle degree. We have a trinomial, and we have a fourth power to second power. We could do the same thing if we had a sixth degree and then the middle was a cubic, or a 10th degree and the middle was a fifth power. So anyway, we can start this by thinking about, are there any GCFs? And then after that, is there a way to pull this apart, thinking about that FOIL makeup, okay? We also want to make sure we set it equal to 0. If we're finding zeros, it means that the y value is equal to 0, which is what I have over here. Okay, so x to the fourth minus 2x squared plus 1 equals 0. I'm going to factor that out by saying x squared and x squared. That was the first thing I thought of. And then if this back term is positive, that says that my factor should have the same operator, meaning both positives or both negatives. And then this guy over here tells us what they both are. So if this says the same, then this says make them both negative, which is what we've done right here. Okay, and then 1 times 1 gives us 1. And if you check that using FOIL, you're going to see that the OI term is that negative 2x squared that we needed. So this is a start to our factored form. Okay, now the next thing I did, and some of you may have skipped here from the beginning, wrote this as x squared minus 1 squared. This squared right here is telling me that any zeros that come from this x squared minus 1 factor will all have a multiplicity of 2. Okay, so think about what that means. A multiplicity of 2, discussed in the previous video. Anything with an even multiplicity, like 2, the graph will touch at that x-intercept, and then it will turn back up. Okay, so the x-intercepts we get, I'm expecting to see touching and turning, not cutting or crossing through the x-axis at these points. There are actually 2 different pathways to get to our zeros, and I want to show them both to you. I don't care which one you do. Both of them are correct, but you have to make sure that you're accurate in whichever path you choose, okay? So path 1, I'm just going to have to show it all to you, and I'll break it down with talking. But we set the x squared minus 1 equal to 0, and then we solve for x. So we're adding 1, and then we're square rooting. The big thing about this path that trips people up is we forget the plus minus. Whenever you take a square root, you don't really know if you squared 1 here to get positive 1 or if you squared negative 1. So you have to put in the plus minus in front. Okay, that's what scares me about this path for you, is that you will forget the plus minus at one time or another. You probably will. I know I have. Okay, path 2. Path 2 looks at breaking this down further. X squared minus 1, you might recognize that as being a difference of squares, and we can break that down a little more. So x squared minus 1 can be broken down into x plus 1 times x minus 1, and the squared that you see here is the same squared that was over there. Okay.
I'm a robot.
I'm a robot. Mason is all dressed up today. Anyway, okay. So now from here, we can set each factor equal to 0, which I should have had there before. All right. And when we set each one equal to 0, we get x equals negative 1 and x equals positive 1. And we don't have to remember to put in the plus minus. So I don't care which path you choose. I personally think pathway 2 is the safer pathway. Pathway 1 will get you the answer if you do it properly. So here's what we have so far. We have an x-intercept at negative 1, and an x-intercept at +1. I know that it may look to you like this is at maybe 2 and -2, but your scale here on this grid is 1/2. So you can see a little 2 forming right over there. This is +1 and that's -1. And I put in the end behavior as well. Okay, and we also expect, we said multiplicity of 2, for it to touch and turn there. We don't know what it does in the middle, but we know it comes down at some point to touch and turn back up there. Okay, that's step 2. Step 3, the y-intercept. Okay, we need to find out what that is. The y-intercept, if the x-intercept is an x value when y is 0, the y-intercept, remember, is the y value when x is 0. So the y-intercept is super easy to find. We're going to set the x is equal to 0 and simplify to get a y-intercept of -1. I'm sorry, +1. So 0, 1 is another point that we can put on our curve. Love you, buddy, but I need you to back up, okay? I only have a few minutes left. Step 4, symmetry. This is the step that I use least often because sometimes graphs have no symmetry. But it is a step that can help you generate your graph, maybe, again, help you know if what you have graphed is correct, okay? So I want to go through this with you pretty quickly. It goes back to being even and odd, which we discussed in a previous chapter. And we have, okay, Mason, listen. That's enough. Thank you. It goes back to this f of -x test, okay? And what I mean by that is we're going to take our f of x function and we're going to substitute -x for all of the x's. And we need to compare what we get when we simplify the right side to the original function. Okay, so we're going to compare f of -x simplified to be x squared, or x to the 4th minus 2x squared plus 1. We're going to compare that to our original. Okay, and here are the rules. You'll have an even function, which means y-axis symmetry. I didn't write that down. You should. If your f of -x is identical to f of x, and that's what we have here. We should have some y-axis symmetry that you're seeing. It's an odd function, or it has origin symmetry. That's like a rotational symmetry. Quadrant 1 and 3 mirror each other, and quadrants 2 and 4 mirror each other. That happens if every single sign has been switched in your function, meaning this would have had, f of -x would have had to have been negative, and then positive, and then negative for that to happen. And then we have a neither situation, meaning there is no symmetry, if you have a mix of some of the signs being switched and some of the signs remaining the same. So even symmetry here. All right, last of all, we have, we talk about the turning points and how many turning points we have. And I've shown you a little chart here to help you see it. Ours is a quartic, and we're going to work up to that. But a linear graph has a degree of 1, meaning that's its exponent. And how many times does a line turn? It has 0 turning points, because a line by definition is straight. A quadratic is a degree of 2, and it has 1 turning point. We call that its vertex. A cubic could have a maximum of, hopefully you're seeing, 2 turning points there. And so that gets us to our quartic with degree 4, and hopefully you see it could have 3 turning points. For any polynomial of degree n, it could have n minus 1 turning points. Okay, so here's our function that we've graphed with our end behavior, our y-intercept, our x-intercept. And it has y-axis symmetry. Looks right to me. Does it have the maximum number of turning points, or at least it can't exceed the maximum number of turning points? And that looks pretty good to me. Okay, so you guys have some practice to do on lesson 3, and that's going to take some time. So please make it through all of your checkpoints for Monday, and then we will work on practice problems together Monday in class.